Welcome to the fourth and final part of this tutorial series where we're using Photon Fusion 2 to build a multiplayer game in Unity. In this video we'll be setting up 3 new abilities which players will be able to use to slow each other down. Before we get into that though, we have a few things to fix. Something you may have noticed after the last video is that when non-host players glide, their movement starts jittering a lot. This was due to an issue with the KCC which has since been fixed, so the first thing we're going to do is update the Fusion SDK and KCC add-on. Start by downloading the Fusion 2.0.2 and KCC 2.0.17 packages. You can find the links in the description. If you're not using version control for this project, you may want to manually back up the network project config and Photon app settings files first so you can restore them later, because the next step is to delete the Fusion and Photon libs folders in the Photon folder. Once those are gone, import the Fusion SDK Unity package you just downloaded. We don't need the Fusion demos folder, so you can deselect that in the import menu. After it finishes importing, I'm going to use Git to restore the resources folder, which contains the network project config and Photon app settings files, to its previous state. Next, delete the KCC add-on from the Fusion add-ons folder. Import the new KCC add-on version. With this version, a few things changed in regards to how the KCC handles look rotation prediction, so we need to make a few adjustments. Open the player prefab and enable the KCC component's force predicted look rotation setting. This setting has changed so that if you want to predict look rotation, it should now be enabled regardless of whether or not the player object in question has input authority. This also means we can remove the line of code that enables it in our player class's spawned method. Down in the render method, we now just need to check is predicting look rotation instead, as this will only return true if this object has input authority. With that done, non-host players should be able to use the glide ability without jittering. I also forgot to implement the player's despawn callback in a previous video, so let's do that now. We'll use this to clear the cameras and UI manager's references to the local player. Since those both outlive the player object when you disconnect from a game, not doing this can cause errors if you're still referencing an object that no longer exists. With those fixes out of the way, let's get into the meat of this video. To start, we're just going to set up the input sampling logic and some of the UI related stuff for the abilities. The way this will work is that all 3 abilities will be activated using the left mouse button, and which one is activated will depend on which ability is currently selected. To do this, we'll need a new enum to represent the ability mode, which I'm just going to put in the player file. The 3 abilities will be breaking blocks, temporarily putting another player in a cage, and giving another player a shove. In the net input file, add a new use ability element to our input button enum, and add an ability mode field to the net input struct. In the input manager's before update method, set the use ability button based on the left mouse button's press state. At the top of the class, add a field to store the currently selected ability. Back in the before update method, we're going to set the selected ability accordingly when the 1, 2, and 3 keys are pressed. Anytime this happens, we're also going to invoke the UI manager's select ability method, which we haven't actually created yet, so ignore the errors for now. Right at the end of before update, make sure to set the accumulated inputs ability mode to the selected ability so that it's part of the input that gets passed to Fusion. Over in the player class, we need to set up all the cooldown related fields and properties. This should look pretty familiar from when we set up the grapple and glide abilities in the last video, so I'm going to move pretty quickly. First, we need fields to store the cooldown duration of each ability. Then we need a tick timer to track each ability's cooldown state. Finally, add properties that convert the remaining cooldown time into a 0 to 1 value so that our UI can use that information later. Down in the reset cooldowns method, make sure to reset all the new tick timers. Next, add a new check abilities method to determine which ability to use when the button is pressed. We're not going to have clients predict the effects of these abilities, so return out if it isn't running on the state authority. Add a switch statement for the input's ability mode, but leave the cases empty for now. Call this new method from fixed update network. In the UI manager, add slider and image references for each of the abilities. Then create the select ability method and use it to enable and disable the ability's selection indicators. In the awake method, call select ability to set the default selection. We also need to initialize the slider values to ensure the cooldown indicators start out invisible. Finally, don't forget to set the cooldown indicators in update based on the corresponding cooldown factors. Back in Unity, assign all the ability sliders and their selection indicators to the UI manager's appropriate fields. If you run this now, you should see that pressing the 1, 2, and 3 keys cycles through which ability is selected. However, nothing happens when you left click, so let's change that. We'll start with the caging ability, so create a new cage script. We'll modify this in a moment. First, open the player class and add a reference for the cage prefab. Add a new networked bool to track whether or not the player is currently in a cage, and then make this part of the condition which determines whether or not the player can glide. The cage's colliders are what will actually prevent the player from moving. Now in the cage class, remove the default contents and make it inherit from network behavior. Add a field to store how long a cage should last before despawning, a tick timer to track the time remaining before despawning, and a reference to the player that is in the cage. Create an init method which sets the caged player and starts the despawn timer. Then from fixed update network, we'll make the state authority check whether the despawn timer has expired, and if so, we'll despawn the cage and set the player free. Back in the player class, add a cage method which will put the player in a cage. Inside, we're just going to spawn a new cage and initialize it, set is cage to true, and break the player out of their glide if necessary. Next, add a try cage method. This will perform all the necessary checks, including if the cage ability is currently on cooldown, and if the player is aiming at an object in range, and if so, whether or not that object has a player component attached to the same object as its rigid body. If we hit a player and the ability is not on cooldown, we can start the cooldown and cage the enemy player. Give the check abilities method a look direction parameter, and then call try cage if the left mouse button is clicked with the cage ability selected. Finally, in fixed update network, pass the cam target's forward vector as the look direction. Over in the game logic class, reset the player's is caged state from the prepare players method. This will ensure that things are properly reset in case a player is caged when the game restarts. In Unity, open the cage prefab and attach the network object, cage, network transform, and audio source components. Assign the prison cell audio file to the audio source's clip field and adjust the other settings as shown. In this case, we'll leave play on awake enabled because we only need to play the sound when the cage is spawned. Don't forget to assign the cage prefab to the player prefab's reference. If you run this now and connect two players, you should be able to use the cage ability to temporarily immobilize the other player. However, the way we've approached the hit detection for the caging ability is flawed. Currently, we're just doing a regular physics raycast. This would be fine in a single player game, but since we're dealing with multiplayer, we need to consider how latency might affect this. If you were to play this with a friend right now, you might notice that caging the other person is harder than it should be, particularly if they are moving. This is because the position at which you see the other player is actually outdated by the time you see it, due to the latency on the connection. In other words, when you see yourself aiming right at someone, you're actually aiming at where they used to be, which is why you miss even when it seems like you shouldn't. To address this, many games where shot accuracy is important employ a technique known as lag compensation to hide the latency. Lag compensation basically has the server store a short history of relevant hitboxes' positions. This way, when a player shoots, the server can rewind all the hitboxes to exactly where they were in the shooter's point of view at the moment that he took the shot, allowing it to accurately detect whether the player hit anyone. While this enables accurate hit detection from the shooter's perspective, the drawback is that the person being shot can be hit for a brief time even after taking cover. But this is typically considered more acceptable and less frustrating than missing a shot you know you should have landed. Implementing a system like this may sound like a daunting task, but luckily for us, lag compensation is a feature built into Fusion and it's quite easy to set up. First off, we need to give our player prefab a special hitbox component, which also requires a hitbox root. Set the values as shown so they fit the player's shape. Make sure the hitbox, shown in yellow, is entirely inside the hitbox root's radius. This should automatically be the case if you click Find Hitboxes after resizing the hitbox, but if you make further changes to the hitbox's size or position, you should double check the hitbox root's radius again too. In the player class, add a layer mask field to store which layers we want to include in lag compensation queries. Then in the tryCage method, change the physics.raycast call to a runner.lagcompensation.raycast. This will require a few adjustments to the parameters as well. For the hit options, we want to use include physx and ignore input authority. This way, the player's lag compensated raycast won't hit himself, and it will be able to hit regular Unity colliders, which includes all of our game's static geometry like the blocks. It's important to note here that this will not hit any player's regular Unity colliders because those are on the player layer, and we will be making sure that that layer is not enabled in the layer mask. Typically, you'll want to attach hitboxes to any moving objects you have in your game, and any objects with a hitbox should have their regular colliders on a layer that is excluded from lag-compensated raycasts. Additionally, instead of checking the hit info's rigid body for a player component, we'll check the hit's hitbox component. Back in Unity, set the player's lag compensation layer mask to only the default layer. Again, this works in our case because all of our colliders which move are on the player layer and we aren't including that. When testing on your own, it's effectively impossible to see if using lag compensation has helped improve hit detection, but if you run the game now, you should still be able to cage other players as before, even though we're no longer using a regular physics raycast. Next, we'll implement the shove ability. Add fields for the sound effect and shove strength to the player class. Then add a networked int which will monitor for changes and use to synchronize the shove sound across all clients. At the bottom, add a shoved method which simply plays the shove sound as a one-shot on the player's existing audio source. Then create the shove method. This just needs to apply an impulse to the player and increment the shove sync value to trigger the sound effect. Duplicate the try cage method and rename it to try shove, since the checks we need to do here are effectively identical. Just make sure to replace the references to the cage cooldown with references to the shove cooldown. We obviously also want to call the target player's shove method instead of their cage method. Finally, call try shove from the check abilities switch statement. Back in Unity, open the player prefab and assign the shove sound effect to the player's reference. If you run the project now, you should be able to shove other players and see them get pushed back. Last of all, we're going to set up the block breaking ability. Create a new block manager script. Then open the block class and make it inherit from network behavior. Add references for the block's collider, model, audio source, and the sound that will play when a block reappears. We also need to store the tick on which a block should reappear, as well as a reference to the block manager. In start, assign the block manager reference. Create a disable method, which we'll just leave empty for now, as well as a hide method. We'll use this to enable or disable the collider and model, and to play the appropriate sound depending on whether the block is breaking or reappearing. In the player class, add a try break block method. Inside, we'll do the usual cooldown check, but this time we're going to use a regular physics raycast instead of a lag compensated one. We could use lag compensation here as well, but since the blocks that we're aiming at don't move, we always see them at their current position, and so there's no lag that we have to compensate for. That being said, if another player were to be between you and a particular block, it is possible that not using lag compensation here could result in that player blocking the physics raycast when it happens on the host, even though on your screen you had a direct line of sight to the block. I decided that this would be rare enough that I'm not going to bother using lag compensation for the block breaking ability, but you could just as well use it here too. Anyways, if we hit something, we'll check if it has a block component, and if so, we'll start the cooldown and disable the block we hit. Then call try break block from the check abilities method. We'll be using the block manager to track and synchronize which blocks are currently disabled. We could also just have each block track its own state, but then each one would need to implement fixed update network and continuously check if it's disabled and whether or not it's time to re-enable itself. Additionally, every client would need to continuously run change detection on every block to stay in sync. Since we have quite a lot of blocks, this could become a drag on performance, so we're going to take a different approach. Instead of each block managing its own state in fixed update network and running its own change detection, having a centralized block manager will allow us to do those things just once per tick. Start by deleting the default contents and making the block manager inherit from network behavior. Add a field for the reappear time. This will determine how long blocks stay disabled for. Then define a constant for the max disabled blocks. This should be set to your max player count, multiplied by how many blocks a single player could break simultaneously based on the reappear time and ability cooldown. Create a network array of blocks with a capacity of max disabled blocks. This will store all of the currently disabled blocks. We also need a change detector, fields for the head and tail elements in the array, and a tick timer. In the spawn callback, set this object to be simulated by Fusion. This will ensure that the block manager's fixed update network method is invoked even on clients where it will have neither state nor input authority. Also make sure to initialize the change detector. Create an add disabled method and return out of it if this is not running on the state authority. In here, we're going to retrieve the first disabled block from the array. This should normally be null because we shouldn't be able to exceed the max disabled blocks amount, but in case it somehow isn't, we will cut this block's disable time short and make it reappear immediately. Then we're going to hide the block we're trying to disable and set its reappear tick using the tick timer to calculate how many ticks from now the block should reappear. We also need to add the newly disabled block to the network array and increment the head value. In fixed update network, we'll start by checking if this is running on the state authority. If so, we need to loop through the array of disabled blocks and re-enable all of the ones whose reappear tick is older than the current tick. After this while loop, return out of the method. If this isn't the state authority, then we need to check for any changes to our array. We'll do this by looping through all the properties which the change detector returns as having changed. Inside the switch case for the disabled blocks property, we need to get an array reader for our array. This will let us retrieve the current and previous states of the array that Fusion stores under the hood in the form of network array read-only instances. Next, we'll use a loop to check each element of the array for changes. With each iteration, we'll take the current and previous values of the respective arrays, and assuming they aren't null, we'll retrieve that block's reappear tick value. Then we can compare these two reappear tick values, because if they're different, then we know that a block has been enabled or disabled since the last time we checked for changes. If this is the case, we'll re-enable the previous block and disable the current block. Finally, we can call the block manager's addDisabled method from the block class's disable method. In Unity, add a network object to the block prefab. Also add an audio source and configure it as shown. Don't forget to assign the block script's fields with the block's other components. Over in the game scene, attach a network object and the block manager to the block's game object. If you run the game now, you should be able to use the block breaking ability to disable blocks, and they should reappear after a few seconds. The final thing we're going to do is make it a little easier to tell if a player or a block is in range by highlighting them with a different color when aiming at them. We'll need two new scripts for this called Highlightable and Highlighter. Highlightable will need a reference to its highlight material and its mesh renderer, as well as a field to store its normal material. We can assign the mesh renderer from onValidate. In start, set the regular material to the one the object is currently using. Create a highlight method which simply changes the mesh renderer's material based on whether or not we want to highlight this object. In the highlighter class, add a field to store the currently active highlightable object, if any. Then create an update highlightable method. Inside, we'll raycast using the player's camera position, look direction, and ability range. If we hit something and the player's grapple ability is not on cooldown, we'll grab any highlightable component attached to the object we hit. Before we can continue, we need to make the player's currently selected ability publicly accessible, so add a property for that to the player class. In fixed update network, we can just set this property to the input's ability mode. Back in the highlighter class, we can now use this property to determine what we should highlight. If the block breaking ability is selected, we'll basically do the same thing as with grappling, except obviously we need to check the correct cooldown. The cage and shove abilities are a bit different because we need to highlight the player, but we won't be attaching the highlightable component to the same object as the collider. Instead, we'll check if the object we hit has a rigid body to determine if it's a player, and if so, we'll grab the highlightable component from the same object that the rigid body is attached to. At the end of the method, and outside of the Raycast's if statement, we can now check if the highlightable is different from the current one. If so, we'll disable the highlight on it, update it, and enable the highlight on the new object. In the camera follow class, add references for the highlighter component and the local player. In late update, call the highlighter's update highlightable method. Then we just need to modify the set target method to assign the player reference. This means that we also need to adjust the places where this method is called in the player class. Finally, back in Unity, attach the highlighter script to the main camera and assign it to the camera follow component's reference. Open the player prefab, attach the highlightable script, and assign the player highlight material and the body mesh renderer to its fields. We also need to attach the highlightable script to the block prefab and assign the block highlight material to it. And with that, hovering over blocks or players with the corresponding abilities selected and not on cooldown should cause them to be highlighted in a different color. That's it for this video, which also brings this series to a close. Hopefully you found it helpful, thank you for watching, and don't forget to like and subscribe.